Have you ever wondered how computers process information? Today we delve into the heart of this question. In the intricate world of computing, a fascinating device known as a Turing machine sheds light on how computers work. Named after the brilliant mathematician Alan Turing, this theoretical device provides a fundamental model of computation. Imagine a machine not like the one on your desk, but a conceptual one. It's composed of four main components: a tape, a head, a state register, and a transition function. These elements, while simple in their own right, come together to create a system that can simulate any algorithmic process. Let's start with the tape. Picture an infinite one-dimensional storage medium divided into cells. Each cell can hold a symbol from a finite alphabet, which includes the input alphabet and a blank symbol. It's like the memory of the machine storing all the information it needs. Next, we have the head. This mechanism reads and writes symbols on the tape and moves left or right along the tape one cell at a time. Think of it as the machine's eyes and hands, interacting with the tape to process information. The state register is like the machine's brain. It holds the current state of the Turing machine. The behavior of the machine is determined by the combination of the current state and the symbol being read from the tape. Lastly, the transition function. It describes how the Turing machine changes states and modifies symbols on the tape based on its current state and the symbol being read. It's like the machine's DNA, dictating its behavior depending on the situation. These components work together in harmony like an orchestra to process information in a systematic and logical manner. They start with an initial state and an input, and step by step they read, write, move, and change states until they reach a halting state, providing an output. So, what is this Turing machine and how does it function? Stay tuned to find out. Picture an infinite tape divided into cells, each holding a symbol from a finite alphabet. This is the first component of a Turing machine. Now, imagine the tape of a Turing machine as a never-ending strip of paper. It's a one-dimensional storage medium, stretching infinitely in both directions. It's not physically possible, of course, but this is a theoretical machine we're talking about. In this world of theoretical computation, infinity is our playground. Our infinite tape is divided into individual cells, just like the squares on a chessboard. Each cell is a tiny storage unit. They're like the smallest lockers in a vast infinite locker room, each holding a piece of information. And what's the information stored in these cells? Symbols. These symbols come from a finite alphabet. This alphabet includes the input symbols, which are the data we're working with, and a special blank symbol. This blank symbol is crucial. It's like an empty placeholder, a sign that a cell is currently not holding any other symbol. Each cell on the tape can hold one of these symbols at a time. Think of the cells as little stages, each hosting a single character from our finite alphabet. These characters can change, they can be replaced, but each cell will only spotlight one at a time. The symbols on the tape are the input for our Turing machine. It's the problem the machine has to work with. It's the question that needs an answer. And just as the tape is infinite, so too are the possibilities. Any problem that can be broken down into symbols from our finite alphabet can be written on this tape. Now, this infinite tape isn't just lying around. It's part of a system, a grand design. The Turing machine doesn't just have an infinite tape. It has a way to interact with it, to read from it, write on it, and move along it. With the tape laid out, it's time to introduce the next component that interacts with this tape. The second and third components of a Turing machine are the head and the state register. These two components play a critical role in the functioning of the machine, setting the stage for its computational prowess. Let's start with the head. Much like the human brain navigating through thoughts, the head of a Turing machine navigates along the tape. This element of the machine can move either to the left or right, one cell at a time. As it traverses, it performs two crucial tasks. Firstly, it reads the symbol presently under it from the tape. Secondly, it has the power to change that symbol, essentially writing a new symbol in its place. Imagine a diligent librarian, scanning through books, reading and making notes. That's the head for you, diligently scanning through the tape, reading and writing symbols. Moving on, let's talk about the state register. If the head is the diligent librarian, then the state register is the librarian's current thought process, the state of mind. It holds the current state of the Turing machine. But what does that mean? Well, the behavior of the Turing machine at any given moment is determined by this state. It's like a snapshot of the machine's current situation. It's the now of the Turing machine. Consider this. You're reading a book and you're at a cliffhanger. Your current state of mind, your now, is anticipation. This state guides your subsequent actions. You hurriedly turn the page to find out what happens next. Similarly, the state register's current state guides the actions of the Turing machine. It determines what the machine does next, whether it writes a new symbol, moves the head to the left or right, or changes its own state. So in essence, the head and the state register work in tandem, like two sides of the same coin, driving the operations of the Turing machine. Now that we understand the head and the state register, let's introduce the final component that governs the machine's actions. The transition function is the final component of a Turing machine, and it's what ties everything together. Picture this. The Turing machine is like an orchestra, and the transition function is the conductor. Every component, from the tape to the state register, follows the precise directions of this maestro, creating a symphony of computation. So what is the transition function exactly? This function is a set of rules that dictates how the Turing machine changes states and modifies symbols on the tape. It can be thought of as the machine's programming, guiding its behavior at each step of the computation process. Here's how it works. At each step, the Turing machine reads the symbol currently under the head. It then consults the transition function, which determines the next action based on the current state and the symbol read. This action could involve writing a new symbol on the tape, moving the head left or right, or changing the state of the machine. The transition function is essentially a table that maps each possible combination of current state and input symbol to a new state, a new symbol to be written on the tape, and a direction for the head to move. Imagine a simple Turing machine that is supposed to add 1 to a binary number. The transition function might specify that if the machine is in the initial state and reads a 1, it should write a 0, move to the left, and stay in the initial state. If it reads a 0, it should write a 1, move to the left, and transition to the halting state. The transition function is what allows the Turing machine to perform complex computations. It's the heart of the machine, pumping instructions through the system, guiding each movement, and deciding the machine's fate at every step. So there you have it. The transition function, a set of rules that dictates the Turing machine's behavior, making it the conductor of our computational orchestra. With all the components in place, we can now see the Turing machine in action. The Turing machine is not just a theoretical model, it holds significant importance in computer science. The Turing machine, despite its simplicity, is a powerful tool that has laid the foundation for the field of computer science. Its theoretical construct has served as a blueprint for understanding the fundamental nature of computation. This theoretical device, introduced by Alan Turing in the mid-30s, has indeed stood the test of time, remaining relevant even in the age of quantum computing. The Turing machine's primary significance lies in its ability to simulate any algorithmic process. It can mimic the logic of any computer algorithm, and because of this, it's often used as a reference model to determine what can be computed. In essence, it's the yardstick that defines the boundaries of computability. Moreover, Turing machines are also instrumental in understanding complexity theory. This is the branch of computer science that classifies computational problems according to their inherent difficulty. By using a Turing machine as a model, we can understand the computational resources, like time and memory, required to solve a problem. Consequently, it helps in distinguishing between problems that can be feasibly solved and those that can't. But the influence of Turing machines extends beyond theoretical computer science. They also have philosophical implications, leading us to contemplate deep questions about the nature of intelligence and the universe. The concept of a universal Turing machine, which can simulate any other Turing machine given the right input, has been used as a metaphor for the universe itself. Some even posit that if a universal Turing machine can, given enough time and resources, simulate any physical process, then the universe itself might be a vast ongoing computation. And there we have it, the Turing machine, a simple yet powerful model that lays the foundation for understanding how computers process information.